In this lecture, I want to look at the stereochemistry implications for the SN1 and the E1 processes. But before I do that, what I want to do is just take a little aside into how we describe stereoisomers for alkenes. Okay, let me just, maybe the easiest thing to do is to just start with what's actually happening with SN1E1 reactions, because that's sort of on our mind right now. So SN1/E1 reactions in stereochemistry. And so in general, what happens is that all possible stereoisomers let's put stereocenters. Yeah, stereoisomers are formed. And there's just one caveat that's pretty small when you see it in the context of structures. But I wanted to at least get this idea in front of us. And then the only exception is except when wedges and dashes do not involve a CX bond. Okay. All right. Small caveat when you see the pictures. But the point is that all possible stereoisomers are formed, and that's for both the SN1 and the E1 reaction. So what we need to do is talk about alkene stereoisomers. And there's a new classification protocol. And that is the EZ protocol. The EZ protocol, and we'll get to that in a second. But what this all comes down to is the idea that alkenes have CC double bonds, carbon-carbon double bonds, that cannot undergo free rotation. They cannot undergo free rotation, okay? And so as a result, if we compare this molecule versus this molecule, okay, these two molecules have the same connectivity and the same number of each element. So same constitution or same composition, which is that they're both, it looks like C4H8, I believe. C4H8 and constitution. And the constitution implies our connectivity. If you recall, constitutional isomers are those with different connectivities. Okay, so we have the same composition, the same number and type of each element, and the same constitution, which is the same connectivity, but these are different structures, and that's because there's no free rotation over CC double bonds. These are different. That is, there's no way we can do free rotation to achieve structures that are superimposable. They are different, and they are different in their orientation in 3 dimensions. Well, structures that have the same composition and constitution, but differ in their orientation in 3D, are, by definition, stereoisomers. I mean, if we have different orientations in 3D, but we don't have different compositions and connectivity, we're not stereoisomers. We're something completely different, right? Constitutional isomers always have different orientations in 3D, but it's when we have the same connectivity and the same number and type of each element, but we differ in how these things are arranged in 3 dimensions that we get to stereoisomers. So stereoisomers are not just wedges and dashes. They're also the orientation of things around carbon-carbon double bonds, because we cannot do free rotation. If we could do free rotation, then we could just interchange these by free rotation, in which case they would be conformational isomers. Okay. So what that means is with stereoisomers, we need a new classification system. First of all, are these two enantiomers? So enantiomers, if you recall, are mirror image stereoisomers. So are those two mirror images of each other that are not superimposable? Definitely not. You can't draw a mirror plane to show that those two structures are mirror images of each other. No way. As a result, they are diastereomers. What are diastereomers? Well, I had this rule about wedges and dashes and some flipping, but not all flipping. But that works. That's a mnemonic or like a heuristic to help you identify when diastereomers are present. But diastereomers in general, the definition is, so I'm going to write big no up here, sorry. Are they diastereomers? Well, diastereomers are non-mirror image stereoisomers. And so are these two molecules that I've shown up above, are they diastereomers? And the answer is a resounding yes. They are stereoisomers of each other that are not mirror images. So they're diastereomers of each other. Now that we've identified the type of stereoisomers that can exist for carbon-carbon double bond systems, what we need to do now is classify these things. So classifying alkene stereoisomers. Okay, so this was a big unit in one of our learning modules. It's kind of blurring together when that was, but a big unit where we had R/S for the Kahn-Ingold-Prelog method. Should we do that again? I mean, it's not too bad once you get the hang of it, but it was several lectures worth of material learning about how to prioritize and rotate and flip and then apply it to more complicated and more complicated and more complicated systems. And then making sure we didn't have counterclockwise and clockwise scrambled. We all bought analog watches, right? No, we actually can't do that in this case. So instead, what we apply are the E and Z methods. The capital E and then capital Z method, not to be confused with the easy method, EASY, but it is much more tractable and manageable to learn and implement than the RS system. So what this is sort of the, oh boy, let me make sure I get this spelling correct. So it is, I'm going to get the spelling right, and I'm going to destroy the pronunciation. So if you know German, feel free to laugh hysterically at me. But E stands for, and really I should put this down here. So E stands for entigen, or Entgegen, I thought. So anyway, I destroyed the pronunciation. This is just German for opposite. German for opposite. And then Z stands for zusammen. So when we have the Z label, we have zusammen, which is German for same. So we really just have opposite and same as our labels, or abbreviated E and Z accordingly. And the reason why it's in German is because, well, German scientists came up with it. So the easy method can be used for any alkene stereoisomer. Okay, so with the EZ method, which can be used for any alkene stereoisomer, we need to keep in mind what they're trying to stand for. We have two labels now, E and Z. E and Z replace R and S. Okay, so we don't use R and S for alkenes. Instead, we use E and Z. And they stand for same and opposite, opposite and same, respectively, I should say. And we'll get to a helpful mnemonic for that. So maybe I'll just say it right now. So E is a vowel, and opposite starts with a vowel. So E stands for opposite. And this is just if you don't know German, which is me. So E, opposite. What about Z? Is there something to help us there? So Z could be used to say Z, same side. Instead of the same side, Z, same side. Or Z, Z, Z. Okay, I've used these over my career. They haven't failed me. All right, so I really like starting with the E and Z approach. It's not the most popular approach, but not for good reasons. And we'll get to that in a second. But E and Z is the best way to label alkene stereoisomers because it works on all alkenes that have stereoisomers. Okay, so what we do is let's pick an alkene that has a stereoisomer to start. So we have this molecule. I'm saying that it has a stereoisomer, which is this. But let's start with this first one here. What we're first going to do is cut the C bond in half at a 90-degree angle. So I'm just going to cut it in half. All right. So now I have like a left side and a right side. Like I could grab this and go left side versus a right side. Whoop, oh, I took too much. Okay. So we have a left side and a right side. Maybe I can do this. There we go. There's my right side. Now, prioritize the groups on each side. Now, what's nice about this is you hear priorities and you're like, oh, okay, that was the hard part about RNS. But we only go up to 2. There's only 2 things attached because the carbons have only 3 things total. One of them is the other half of the alkene. We don't prioritize that. So as 1 or 2. So what I'm going to do is focus on the left side. Now we have 1 for the methyl group because the the hydrogen gets 2. Now on the opposite side of our alkene that we cut in half, we have 2 for the hydrogen and 1 for the methyl group. So you only have 2 groups that you have to prioritize. You only go up to 2 and you just do it on each side. Now we're almost done. 3. If the 1s are on the same side, well, Z same side is Z. Z same side. However, if opposite, then we're E, because opposite starts with a vowel, O, and E is a vowel. Okay, so what do we think? Well, if we look at our original molecule, and I draw it nice and big here, and I say let's look at the 1s, but we could also look at the 2s, right? So in this case, the 1s and the 2s are on opposite sides of each other. The left side, the 1 is on top, and on the right side, the 2 is on top. So we have opposites, and as a result, this is an E alkene. So we would label that overall carbon-carbon double bond as E. We don't put it at each of the carbons that comprise the double bond. We just say it's an E alkene. I usually put it over the bond in case there are multiple carbon-carbon double bonds. So that's it. That's labeling things as E and Z. let's do a few examples. So let's say we've got, I think it's always healthy to look at a ring structure. Okay, let's pick a molecule with complicated groups. Let's pick a molecule with multiple double bonds. Let's pick a molecule with two of the same group on either side. And then let's pick a molecule with non-carbon based atoms. Okay. All right, so let's look at each example here. In this first example, I'm going to cut the carbon-carbon double bond in half. And I'm going to label, I'll stay red, sure. So the rest of the ring gets 1 over the methyl group, which gets 2. I'll add the hydrogen, which gets 2, compared to the rest of the ring structure, which gets 1. So this, we have the 1s on the same side. In this case, they're both pointing left because the alkene is tilted into a different rotation state, but this is a Z alkene. Now we move on to the next one. So we cut this in half. The big isopropyl group gets 1, the little methyl group gets 2. But on the right side, we have a hydrogen, which always gets 2 compared to the methyl group, which gets 1. This again looks to be Z. We've got 2 alkenes in this next example, so we'll cut both of them in half at 90 degrees compared to where the alkene is drawn. So we have 2 for the hydrogen. Both of those are on the same side. So I'm going to apply a Z label. I'm going to put it nearby the double bond so that it's clear which double bond I'm labeling, because there's actually 2 in this case. Now for the other carbon-carbon double bond, we have 2 hydrogens. Both of them are the 2 priority and they're on opposite sides. So that appears to be E. I'm going to put that E close to the alkene so I can tell which is E and which is Z for the 2 alkene system. Now over here, I'm going to cut this in half. We have a hydrogen with a 2, a methyl group with a 1. Okay. Now on the left side, you'll notice that we have a CH3 and a CH3. Which of those is 1 and which is 2? I cannot prioritize. The rule is broken down in the 4th example that we've looked at. Willoughby said this worked for everything that has stereoisomers at carbon-carbon double bonds. And it's true. This molecule does not have stereoisomers that are carbon-carbon double bonds. If you think about what the focal point of the stereoisomers was, it was when we sort of repositioned a group for, instead of being up, as being down. So I'm going to do that. I'm going to reposition the group that's on the right of my cut to be down. But if you look, these structures are the same. So the E and Z assignment is not applicable. Okay, same. So if these 2 are the same after flipping that group, or if either the left or the right side, whatever, after we cut it in half, have the same groups attached to it, we just don't have stereoisomers. No alkene stereoisomers. So the answer is not applicable in this case. And that would work if we had 2 hydrogens at the end. So many cases we would have complicated molecule, methyl group, and then we just leave it like this. And if you went to assign it, you'd be like, oh, there are 2 hydrogens here. So this is also not applicable. Okay, I like to throw those examples in. Let's go up to this one. Now we have 2 and 1. On the left side, we're comparing an oxygen, which in the RNS nomenclature got the higher priority. That carries forward with E and Z. And so this appears to be an E alkene because the 1s are now on the opposite side. Okay. So that was fairly quick, but it's not too bad, I would argue. Now, what we should also do, we would be remiss if we didn't talk about, is the alternative and less good way to describe alkene stereoisomers. That is to say, there are many examples that of alkenes that have stereoisomers for which this method doesn't work. And you might say, if that's the case, then why tell it to me? if I'm never going to use it? The problem is you will use it. In a lot of very important circumstances, this older, less good approach is used, and I don't really know why. Because it's very simple to switch back to E and Z, a system that works for everything. But whatever. This is the cis-trans approach. And we've talked about cis-trans in the context of relative configuration of cyclic alkanes that have substituents hanging off of them, right? So cis is same, and then whereas trans is opposite. And so what we see for alkenes is that if we have our two approaches here, we would call this one with the methyl groups pointing in the same direction as cis, and the one where they're pointing in opposite directions is trans. But the reason why we label them as cis and trans is not because of the methyl groups or the groups at all. Rather, it is all about the hydrogen atoms. So when we have hydrogen atoms attached to both ends after we cut in half, we say that if the H's are on the same side, then it's cis. And if the H's are on opposite sides, then it's trans. Okay. This less good approach only works when each CC double bonded carbon atom has one H atom. Okay, so if I had this, you would say that that is trans. Why? Because there are, I know this is the example I just did, two H's. But if I had this, you would say, well, if you wanted me to figure out what that is, I would just cut it in half, label 1, 2, 1, H is 2, and I would say that that is Z same side Z, which is equal to cis, right? Wrong. Cis only works and trans only works when each of the carbons that are double bonded to each other have a hydrogen each, because cis and trans look at only the relative orientation of the two hydrogen atoms. And I know it's like super pedantic. Why didn't they just use the words cis and trans for E and Z? I get it. It is very weird and annoying. And I wish it was just that E and Z were cis and trans, but it was actually first discovered and developed by the Germans, or German scientists, I should say. So we should certainly give them credit. But let's look, where is cis and trans used today? And the answer is in various places in lipid biochemistry or fatty acid biochemistry. That is to say, we looked at how fatty acids could be detergents. They have this carboxylic acid head group. And what we can do is we can add double bonds at various places, and we call that a site of unsaturation, because it's not saturated or full of hydrogen atoms now. We could add more hydrogen atoms. It could be more saturated. So this is an unsaturated fat, site of unsaturation, excuse me. So this is an unsaturated fat pictured above. With a, let's do it. The H's are on opposite side with a trans alkene. And so when this fatty acid with a trans alkene is locked up as a triacyl glyceride to form a lipid or a fat, this will form a trans, gosh, killed my punchline there. This will give us a trans fat. So I'm sure that many of you have heard trans fats and why they're bad for you, or if you haven't, yes, trans fats are really bad for you. And then there are unsaturated and saturated fatty acids that build up saturated and unsaturated fats. That's where this all comes from. We're all talking about the number and stereochemistry of the alkenes that comprise the fatty acids, that comprise the triacylglycerides, that comprise the foods that many of us are consuming and then building up. Okay, so we use cis and trans a lot in to describe fatty acids, which again are important for fats, and lipids in biochemistry. So that's where this is used, and it's used extensively. People often don't say cis fats, which always kind of intrigues me. Sometimes they say non-trans fats, and I'm like, just say cis, or even better, say Z or E, because then it would work for everything. Okay, with that, let's wrap up this lecture by talking about the stereochemistry of SN1E1 processes. That is to say that all stereoisomers form. Okay, so what I want to do is consider a reaction where we do this, and we treat this with an excess of methanol, CH3OH or MEOH, or this. It's all the same. So what I'm going to do for now is provide you with the products, or maybe I should wait until we go on to the next page. Let's go ahead and look at the next page. Okay, so if we practice this, the first thing that we want to recognize is that, sorry, I'm going to flip back to have a methyl group. Yeah, the methyl group as a dash and a BR as a wedge. Okay, so the first thing that happens in this reaction is that the bromine leaves. That's going to give rise to this molecule here, which has a positive charge plus Br minus. Now, what I want us to realize is that while our starting material was chiral and a single enantiomer, the intermediate, the carbocation, is achiral. It no longer is not superimposable on its mirror image. Actually, it's flat. The plus charge is sitting at a carbon that no longer requires a wedge and dash. We can draw everything perfectly parallel to the piece of paper. And so now the methanol will add and what you could think about is the methanol could add on top. So if we have this like molecule that's flat and is parallel to the piece of paper, the methanol could come from this way. And if the methanol comes from this way, the substitution product is going to have a wedge at the oxygen that's doing the attacking. So if we have top attack, we would have CH3H. Can you head out of here, bud? Please? Thank you. To give this molecule with a wedge, I don't know what else is a dash, but it doesn't matter because we could also have bottom attack. If you want to think about it as backside attack, that's fine. It's all inconsequential because both of these approaches to attacking the carbocation are going to give rise to, while they give rise to intermediates that are enantiomeric, one has a wedge and one has a dash, okay, we're going to get a 50-50 mixture of both of these. So both happen, and a racemic mixture forms. So both happen and a racemic mixture forms. What I want to do is skip down to the next step of the mechanism where the hydrogen just gets lost. I'm going to show the electrons jumping from the oxygen-hydrogen bond onto the oxygen atom to lose H+. And if both of them lose H+, we're going to get neutral structures, one with a wedge, the CH3. Now the trouble with what I'm drawing is when I draw one with a wedge and one with a dash, I still don't know what the orientation is at the other stereocenters, right? I mean, honestly, I could just pick one to push forward and backwards. Let's just pick the methyl group. That's the easiest one to draw. Okay. But we have a 50-50 mixture of both of these. And so we might as well just draw the molecule without a wedge or a dash at the stereocenter. We've generated a stereocenter, okay, from an achiral intermediate, which was the carbocation, but we did so with a 50-50 or 1-to-1 ratio of both possible stereoisomer products. So just draw the product without a wedge or a dash. And that will show us that we formed the racemic product. So when you're asked to predict the products for the substitution products, you don't only need to draw one product, and that's the one where the wedge or the dash at the halogen center has just been replaced with straight lines. And when you do that, you just imply to people that, you know, we get both stereoisomers, or we don't know the absolute configuration of that particular position. We have a 1-to-1 ratio, okay? So you only need to draw one product. Now, this doesn't affect stereocenters that are not part of the halogen. And we'll look at examples of that in future lectures, but I'll just mention that now. But what about the E1 products? Okay, here what we want to draw is all E or Z isomers should be drawn, because you form all E or Z isomers. Okay, so if this was our achiral carbocation intermediate, we could lose a vicinal hydrogen, which I've labeled as HA, and there are 3 possibilities. And that would give rise to this, which I'll call as product A. And this results from loss of any HA. Now, similarly, we could form carbon-carbon double bonds from losing the vicinal hydrogens, which I'll label down here as HB. However, one would give rise to a what looks to be E product, and then another one would give rise to a Z product. Okay, so here both are formed. So the final answer for this question of predict the products is if we started with a single enantiomer of a chiral molecule that looked like this, and we reacted it with methanol, which was the solvent and the nucleophile in a solvolysis SN1E1 reaction, what we form are substitution products, and it's a 1-to-1 mixture of 2 enantiomers, but we just draw it with straight lines to imply that we form just the one enantiomer along with all possible E1 products. So this was product A plus the E product B. Actually, I should flip that around. I should put the E in parentheses, and then product B as a Z isomer. And then I'll just mention this. What if we put the alkene going off to the tert-butyl group? That does not form. We do not have a vicinal hydrogen there. I'm going to cross that out so you can see it. We do not have a vicinal hydrogen at the other carbon. And as a result, we cannot form a carbon-carbon double bond. And if you look at that product and inspect it carefully, you see that we break the octet rule to the carbon atom that is double bonded, that is part of the T-butyl group that gets double bonded. Okay, so in this lecture, we did a deeper look into the stereochemistry of the SN1E1 reactions. So you should know that all stereoisomers are formed and be able to draw all of them. For the SN1 product, it's quite easy. We leave the wedges and dashes alone as straight lines to imply that we have a racemic mixture. For the carbon-carbon double bonds, we want to recognize that if we can form a Z isomer, then we can also form the E isomer, and vice versa. If we can form an E isomer, we can also form the Z isomer. So inspect your alkene products carefully. Make sure you don't miss any E or Z isomers of alkenes that could form with that have stereoisomers. In addition to all of this, we broke down and looked at how to classify alkenes as E and Z stereoisomers, as well as cis and trans, but E and Z is by far more important. Maybe there'll be one question on an exam that's like, hey, is this a cis or a trans alkene? Just so that we can say that we know it. It's helpful to know. People know and use that nomenclature, but E and Z is way more important because it can apply to every alkene that has stereoisomers. So with that, I'll wrap up this lecture. Hopefully we can do some practice on SN1E1 reactions from the discussion problems in a future lecture.